Welcome. In this video of our series on diffusion image filtering, it is the first time that we'll actually apply a diffusion filter to an image, which is very cool, yeah? So we're gonna take a look at the two-dimensional heat equation, which we are going to, and then we are going to use this two-dimensional heat equation on a real image using an image as an initial field configuration. Yeah. Okay. So first of all, there will be some theory here, but you should all be aware this should be familiar if you studied in any STEM course on calculus of several variables. Most of this stuff here is pretty much what we did in the 1D case with some products, right? Because you need to have now 2 dimensions instead of 1. And most of this theory is like just notation, right? But we'll go through it anyway because it is important. There are some subtle differences that we should be aware of. But overall, it is pretty much a straightforward extension of the 1D case. Alright, so we set up in the 2D heat equation. Now our field, before we have u of xt, now we have u of xyt, right? And the heat equation now reads del u del t equals d, the Laplacian of u, right? And the Laplacian of u is given by this formula. It is simply the second derivative of u with respect to x plus the second derivative of u with respect to y. And again, as before, we have an initial field, we define it at time equals 0, and then we have this f of xy function. F is now a two-dimensional function instead of 1D1, right? And then all of this stuff should be familiar from calculus of several variables. When we have a 2D function, in this case a scalar field, right? Because it is a function that takes a point in 2D and returns a number in 1D. We have that the gradient of u equals the partial derivative of u with respect to x in the x direction plus the partial derivative of u with respect to y in the y direction. And we sometimes write this position vector as r, which is the x-coordinate times the unit x vector plus the y-coordinate times the unit y vector, right? And of course the absolute value of this vector r, if you are not familiar, this bold font usually denotes a vector, and then this normal or italic font denotes a scalar, right? So it's important to distinguish them. Okay, so now the asymptotic boundary conditions that we have before, they are now imposed for a large R. We now want the limit of the field for a large absolute value of R to vanish, and also the limit of the modulus of the gradient, of the absolute value of the gradient to vanish at R infinite. And then again, also a common abbreviation that we're going to use. We're just going to write integral of d2r is just an integral in the x-coordinate from minus infinity to infinity times an integral of the y-coordinate from minus infinity to infinity. Alright? Cool. And then just as before, in the one-dimensional case, we had the total conservation of the field, or the conservation of the total amount of field as the equation evolves. And here we have the same thing, and this is just the proof of it, because we can set up this integral over all the space, and when we differentiate with respect to time, we arrive at this, which is the integral of the Laplacian of u, rt, and one of the things that we're going to see before, that the Laplacian is equal to the divergence of the gradient of u, And we have like the divergence theorem in 2D. It says that if you integrate the divergence of something in a surface, this is equivalent to integrating the that scalar field, that vector field, sorry, scalar product with the normal of the surface that surrounds it. Again, I will not go into details on this. If you've never seen this, please go to any vector calculus course. But what essentially this does is, because the modulus of this gradient, if the absolute value of this gradient falls fast enough, as r goes to infinity, this here will become 0 and this thing will conserve, right? Oh, and then here is just the the divergence of vector field. See, now that is f is bold, which denotes a vector, and a vector field is nothing more than two scalar fields, one for each coordinate, and the divergence of this field is simply the partial derivative of the x component with respect to x plus the partial derivative of the y component with respect to y. Yeah. Okay. And just like we had a Gaussian in one dimension, we have a Gaussian in two dimensions, which is straightforward. We simply multiply a Gaussian in the x direction with a Gaussian in the y direction. And then here we have this, which is 1 over 2 pi sigma square, the exponential of minus x squared plus y squared divided by 2 sigma square. And since this here is equals to r squared, the absolute value of the vector, we usually write this as e to the minus r squared divided by 2 sigma square. And the two-dimensional Dirac delta, just the same as the Gaussian, it is just the multiplication of a Dirac delta in the x direction times the Dirac delta in the y direction. And just as before, if we do the convolution of the Dirac delta with any other function, we get the function itself. So this integral of r prime delta r minus r prime d square r prime is just equal to fr. You can like open this integral if you want to. It will be one integral in the x direction, one integral in the y, and we should be done, right? And now when we go to Fourier space, we no longer have a frequency number, we have a frequency vector, right, which is just a vector k, which is the kx component times x plus ky times y. And there is a 2D Dirac delta identity, just like the 1D one, which is the integral of the exponential of minus I k. The scalar product, this dot denotes the scalar product, which is just you pick the product of each of the components and sum them. Again, vector calculus. D squared r equals 2 pi squared delta k. And again, this is just like you can break this up into 1D integrals, evaluate them, and package them all together, right? This is just notation, right? And so, just as before, we can define the 2D Fourier transform, and this is f of k equals the integral of fr e minus I k dot r d squared r, right? And from this frequency function, we can get back the position one. So, well, this is just the proof that f of r equals 1 divided by 2 pi squared integral of f k e I k dot r d squared k. And then, just as before, convolution in position space corresponds to pointwise multiplication in frequency space. If we do, well, here I did not copy the derivation in the 1D because it was too long, but it is like the same thing. You break it up into two one-dimensional integrals, and then if you pick like this thing, we'll have that the Fourier transform of the convolution is just the product of the Fourier transforms of each of the functions, right? And, well, so far we only discussed the Fourier transform of a scalar field, which is a function from R2 to R. R denotes the real plane, right? But there is the Fourier transform of a vector field where you take a vector and then you return another vector, right? And this is simply, well, since a vector field is just one scalar field for each component, the Fourier transform of vector field is completely analogous. It is just the Fourier transform of each component in the same direction, right? And what happened is that, if you remember, in the 1D Fourier transform we had a relation for the Fourier transform of the derivative, and in this case we have relations for the partial derivatives as well. So the Fourier transform of the partial derivative with respect to x of f is just I kx times f of k. And the same thing for the y component, del f del y. When you transform this, it will be I k y f of k. So because this thing for the derivatives exists, we have identities for the gradient and the divergence of a vector field. So the Fourier transform of the gradient is just I times the vector k times the vector field. It's I, the vector k, times the scalar field f, and the Fourier transform of the divergence is just ik, the scalar product with the vector field, with the Fourier transform of the vector field, right? And since the Laplacian is just the divergence of the gradient, we can apply this identity, and then we will find out that the Fourier transform of the Laplacian is just minus k squared times the Fourier transform of the field, right? And well, so now once we did all this we introduced all this formalism, the problem kind of solves itself, right? Because if we have the heat equation now, del u del t, so we take the Fourier transform with respect to x and y, and what's going to happen is that del u del t, u in frequency space, is now equals to minus dk squared ukt, right? And this is just an ordinary differential equation, and the solution is simply ukt equals uk0, the exponential of minus dk squared t, right? And again, we can express this as a 2D convolution with a heat kernel, which we obtain when we simply Fourier transform this multiplicative component, and then this is just 1 divided by 2 pi squared integral of the exponential ik dot r minus d k squared t d squared k, right? And as before, this kernel is just a Gaussian, and it's a 2D Gaussian. We will not go through the derivation here, but it is 1 divided by 4 pi dt, the exponential minus r squared for dt. But now notice that although we have the standard deviation of the Gaussian, which is square root of 2 dt as before, however, the size of the Gaussian, the width, now is no longer the expected value of x squared or the expected value of y squared, which would give this variance sigma squared, and then we would take the square root to obtain the standard deviation, right? This now we need to the expected value of r squared, which is the sum of x squared plus y squared. And for this reason, while we in the 1D case we had that the width of the Gaussian was the square root of 2 dt, now in 2 dimensions the width is 2 square root of dt. The formula is different, right? Because of this detail in 2 dimensions. We have 1 dimension more to compute. This is an important difference, right? And well, one can of course obtain the solution. It is just urt. It is equal to the convolution of ur prime at time 0 with the kernel r minus r prime at time t. We compute this convolution and we have the solution to our equation, right? Cool. So now we're going to go back to the discrete spectrum, right? So this is a solution for the continuous, and if you remember our theoretical treatment in the 1D case, the discrete Fourier transform arise when we impose periodic boundary conditions, and the same is true here. So instead of imposing asymptotic boundary conditions, we're going to impose periodic ones. And what's going to happen is that we set up this thing on a, before we had an interval, right, between minus L and L. Now we'll have a rectangle, which is minus Lx to Lx and minus Ly to Ly, the first in the x direction, the second in the y direction. So, and we require that both the function and its spatial derivative in that direction, they vanish at these points, right? And then if we solve the heat equation with separation of variables, what we're going to have, it's just like analogous to the case we have t prime divided by t equals d x double prime x plus y double prime y, and as before, these things, they should be constants. So we should have x double prime x divided by xx equals minus kx squared, y double prime y divided by y equals minus ky squared. As before, we chose the sign to obtain a non-trivial solution, and then once we do all the boundary condition stuff, just as in the 1D case, we'll have kx equals nx pi divided by lx and ky equals ny pi divided by ly. And now, if you remember from the 1D case, we had sines and cosines, and then we could package them all using using complex exponentials. And we're going to do the same here. We will assume that the field can be complex. We would be solving a more general problem than the one where the field is real, but it turns out that this problem is easier. So what happens is that instead of using sines and cosines, we're going to use complex exponentials, right? And it turns out that when you use complex exponentials, this n here, it makes a difference if it is positive or negative, right? So the general solution would be, this is important, nx runs from minus infinity to infinity, not 0 to infinity, and ny the same thing, and then we have a constant for each of nx and y, and this complex exponential here. Alright, and then if we just evaluate as before, these integrals of these exponentials, they are orthogonal, just like integrals of sines and cosines. What we're going to find is that these coefficients then can be found by simply evaluating a two-dimensional integral of the function f with the corresponding exponential, right? And now we are actually not working with a continuous function. We have a sampled field, and there is no reason to choose a different step size in the x and y directions. So we'll call these step size delta r, and then we set Lx equals nx delta r and Ly equals ny delta r. Okay, so when we do this, we have now, if you remember from the 1D case, we were limited by the Nyquist frequency of the signal when we were going to sum of frequencies. And here what's happening is that the Nyquist mode needs to be sampled only once, right? So the Nyquist mode, in minus nx or nx, they are the same thing. It doesn't matter which one you choose. Here I chose the negative one. So we have to sum from nx equals minus large nx to large nx minus 1. Same thing on y. And we have here. And if we define the frequency vector as nx pi divided by large nx delta r x component, same thing for y, and we take the position component equals mx, like this thing, and then with the sampled, this mx is where the sampled signal is evaluated, then we can simply write that the function is the sum of all possible k vectors of these a components times ei, the scalar product of k dot r. So we see something analogous to the Fourier transform emerging here. And again, if you remember in the 1D case, we had to approximate the integral by the trapezoidal rule, right? And then if we do the same here, we get like the sampled signals, and then after the dust settles, we have a n x and y equals 1 divided by 4, large n x, large n y, sum over all r's, f of mx and y e minus ik dot r, right? And if we, after we compute the A coefficients, we can add the time dependency, that exponential factor that we talked about earlier, to solve the problem. And we can, of course, simplify this exponential, because we can substitute the value for kx squared, and then it will be the exponential minus dt pi squared divided by delta r squared equals nx squared divided by nx squared plus ny squared divided by ny squared, right? And this is essentially the FFT in 2 dimensions. Like we have this summation over k and this summation over r here, the FFT in 2 dimensions. And then if you remember, the FFT is not actually defined with a sum starting from negative modes like this, from minus nx to nx minus 1. It's actually from 0 to something. But it turns out, because of these I pi things here, it doesn't really matter if you, well, just keep summing here on positive things. So if we do like this simplification, we can write AKL equals sum of n equals 0 to n minus 1, sum of m equals 0 of m minus 1, fmn exponential of minus 2 pi I, and k divided by n plus ml divided by m. And this is exactly the discrete Fourier transform. And when we compute this with the FFT, we can compute fmn, the solution at a time t, with, it is the inverse Fourier transform of this, but now multiplied by this thing here. And the only thing that we need to take care of, now we wrote n, which is double our signal, right? Because as we see before, we're gonna have to like flip the image to actually use the FFT correctly. And then we see here that we have this exponential factor, but notice that because of when this nx squared here, it is not exactly n, the variable that is being summed. Oh, it should actually be k here. Alright, it should be, yeah, I will fix this later. It should be k and n minus k and l and minus l, but we need to do this minimum here because this value is not an absolute frequency. It represents a negative frequency, right? That's what we should use. Okay, so that's pretty much all the theory. So what is actually this formula? As you can see here, we could express the solution only in terms of the sampled things. So for example, the number of samples, which is m and n, and the value of the field that is sampled at those times. And in the image setting, this is like the values of the pixels, right? And then we have this exponential when we have this factor here for dt divided by delta r square, which we need to choose. And this makes sense because if you think of it in an image, you have only pixels, right? You don't really have a continuous values to refer to. For example, your Lx, where you're imposing your boundary conditions, it can be anything, really. So this delta r here, it kind of represents what is the distance in real space between the pixels of the image, which you can choose. You can like pick any value you want. But in practice, you're actually going to choose this value depending on, we'll see that the effect of the linear to the equation on an image is to blur it, right? And then the larger the size of the Gaussian, the more you blur it, right? So for example, if you pick this value 40t divided by delta r squared equals 1, it means that your blur will be more or less of the width of 1 pixel, which is almost nothing, right? And if you put like 10 or 100, then you have a much more aggressive blurring in this. Well, yeah, because if you put 10, since the width will be like 2 square root of dt, right? So if you put this guy 100, the blur will be 100 pixels. That's all that's being said here. Well, without further ado, let's go to Jupyter. I'm now calling Python in Jupyter because it is easier to show images. And then here we have the Lena image, a classic image used in image processing. And what we do, we take only the grayscale, we convert it to grayscales and it becomes like this. And then when we convert it to grayscale, we have only one scalar field, right? Because before we had 3 channels, R, G, and B, and now we have only one, which is the difference between black and white. And we're going to run the heat equation using this image as the initial configuration. And then the first thing that we do, if you remember what we need to do in the 1D signal, if we wanted to use Dirichlet boundary conditions, we would need to flip the signal, complete the signal with an odd function and apply the fast Fourier transform. If we wanted Neumann boundary conditions, right? If we wanted Dirichlet boundary conditions, and then if we wanted Neumann boundary conditions, we needed to complete it with an even function, right? It turns out that for images, since to use Dirichlet boundary conditions, you need 0 at this. We need everything to be black, right? And it could be used. It would look a bit weird because every image would have to have a black border for you to apply this, but you could do. But it's usually a better idea to use Neumann boundary conditions because they preserve the total field just as you would expect from the continuous case. But in the end, it doesn't really matter. If you use very, very low blur, it wouldn't. Oh, so why? Okay, so I think there was a problem evaluating it. And then, okay, so what happens is that when we concatenate the image, you see now we're going to use Neumann boundary conditions. So we want to first flip the image in the y-axis and then flip the resultant one in the y-axis, and then we have this kind of crazy effect, right? So what we do, we then evaluate the FFT, and then we do this. You see, we at this, when we construct the signal to convolve, we do that mean function that we did in the node, that we found in the nodes. We set up the signal, and then we take the inverse fast Fourier transform at that space, right? And then, so when we retrieve the image back, we only pick this part. And if you see the result, this is the original image, this is the new one. And you see it had kind of blurry effect, and you can control the amount of blur, right? Here we have minus 25, which means that the blur is around 25 pixels. If I put minus 1, it shouldn't really. So I think there was an issue because it's picking the colored one for some reason. Okay, now it's picking the grayscale one. You see here we see almost no difference because the blur is very small, only 1 pixel. But if we put 10, you will start to notice that the image blurs out more. Then we can put 25 for a much more aggressive blurring. And well, if we put a crazy high value like 1000, yeah, you see that the image is just pretty much gone, right? Well, that's all for today. We saw now how we can use the 2D heat equation to apply a filter for an image. And then in the next videos, we did this with the exact procedure with the fast Fourier transform. Then in the next videos, we'll see how we're going to do it with the approximation methods that we developed in the other classes. All right? Until there, goodbye and see you in the next one.